Hello, welcome to this lesson of our study of mathematical proof, and that's what we call the integer modulo n, or congruence of integers. Now, given integers a and b and a natural number n, we say a and b are congruent modulo n if a n divides a minus b. I normally use this in my mathematical proofs. When we say something divides another number, if I say a divides b, or maybe let me use two different x divides y, means that y can be written as x multiplying some integer. Okay, so if I say n divides a minus b, it means a minus b can be written as n multiplying some integer. Okay, now an example is we say that 9 is congruent modulo, or maybe when we say that, then we can write it as a is congruent modulo. A is congruent to b modulo n, or b modulo n, or something. So with this example I have here, 9 is congruent modulo to 1 mod 4, because we can see that 4 is divisible by 4 divides 9 minus 1 actually. So 4 divides 8, and it's true because 8 can be written as 4 multiplying some integer, which is 2, right? So these things works. And on the other hand, you can also say that you can use the idea that with modulo, it means you just find what you get when you divide 1 by 4. You get 0, remainder 1, right? So you get 0, and then the remainder is 1. What did I just write like that? I mean, it cannot divide it wholly, but the remainder when you divide 1 by 4 is that you get a remainder of, okay, so let me say we'll give remainder what's 1. Now you compare with when you divide 9 by 4, you get 4 plus 1 over 4, so it means you're gonna get 1, as a remainder as well, because when you divide 9 by 4, 4 can goes to 9 4 times. I'm sorry, did I say 4? 2 times, and then remainder 1. So in other words, if I say a is congruent modulo to b mod n, what I'm trying to say is that both a and b leaves the same remainder when they are being divided by n. Okay, so that's the whole idea. Now a counter example is that 14 is not congruent modulo to 8 mod 4, because 14, did I say no, 4 is not divisible, or maybe 4 does not divide 14 minus 8. Now 14 minus 8 is actually equal to 6, and 4 does not divide 6, because you cannot write 6 as 4 multiplying a certain perfect number, right? So that's the whole idea. Now let's look at some basic proofs that arises as a result of congruence modulo. Alright, so if you have a, b being integers and an n as a natural number, if a is congruent modulo to b mod n, then we can say a squared is also congruent modulo to b squared mod n. Now we're going to write this as a direct proof. Suppose that a is congruent modulo to b mod n. Then we know that n is divisible, or n divides a minus b, meaning a minus b is divisible by n. That's something that normally confuses, but try to get it along as some teaching. All right, so n divides a minus b. That's it. Means that a minus b is equal to some n multiplying an integer where k is the integer, right? Now if I multiply each side by this number a plus b, what will I get? I'm gonna have a plus b and k, right? And this will mean that a plus b multiplying a minus b from basic algebra is the same as that, and this is also equal to a plus b multiplying k times n. But what is this? A plus b is an integer, k is also an integer. When I multiply them, I'm going to have an integer. Alright, so this is going to be p n, where p is equal to a plus b multiplying k, and it's an integer, right? Now, what does this tell us? This basically is a definition of congruence modulo, right? Okay, I didn't write. Let me explain it here. What this means is that we can write a squared minus b squared as a multiple of n, or as something multiplying n, meaning that n divides what? A squared minus b squared. But that is exactly the definition of congruence modulo. If n divides a minus b, it means a is congruence modulo to b mod n. So if you have n divisible by this, it means that a squared is congruent modulo to b squared mod n. Alright, that's a basic proof. So very simple, right? Now let's go to the other one. If 12a is not congruent modulo to 12b mod n, then n does not divide 12, right? So here we cannot just prove this straight away with the negation in them. So we can try to write a contrapositive of this. Contrapositive of it is that we negate this and negate that. So the negation of this guy implies the negation of that guy. So when we negate the other one, you're going to get if n divides 12, then we can say that 12a is congruent modulo to 12b mod n, right? So that is the whole idea about this contrapositive. Now I can then prove this contrapositive statement. So if I'm able to prove this, then it's equivalent of proving this guy, because we just learned out of the contrapositive that to prove a statement or a proposition is also equivalent to proving the contrapositive of it, right? So suppose that we are proving the contrapositive. Suppose n is divisible by 12, or sorry, n divides 12. Kindly forgive me. That means 12 is actually divisible by n, not n rather. N divides 12 implies that we have 12 being written as n times an integer, right? Now, I want to create something here so that I can get 12a minus 12b, equals n multiplying something. So I can try to multiply each side by a minus b, right? This is going to give me 12a minus 12b, a minus b multiplying k, then n. Now the whole of this will give me an integer because a and b are integers, right? So I'm going to have 12a minus 12b equal to some integer q multiplying n, where q is equal to a minus b multiplying k, an integer, right? So I have these relation. This is definitely the idea that n divides 12a minus 12b. But wait, this is also the definition of integer modulo, right? So this means that 12a is congruent modulo to 12b mod n. So since we've been able to prove the contrapositive, it means this statement or this claim is true, right? So that's the proof for all these. Stay tuned. I'm going to do other videos on congruent modulo. In fact, with the other previous one that we did here, we can prove that a to the k is actually congruent modulo to b to the k if a is congruent modulo to b mod n. This relation holds, and I'm going to prove that maybe in our next 2 videos or something. I'm going to do other proofs as well. So yeah, thank you, and don't forget to subscribe to my channel if you have not subscribed. See you.